Tech people, are we good? Hello. I think we're good. Hello, everybody. Mick has given me the impossible task of getting through and chairing 5 presentations in an hour. And when he did this, he said, it's all going to be fine because when you add them all up, they only come to 58 minutes. So we're going to be good. We're going to just, I think the 2 clocks are not in sync. But hi, I'm Richard from PHF Science, so I'm a senior data scientist. I'm talking tomorrow, so I'm just going to really hand straight over to Wei, who's got their first talk, so straight over from NVIDIA, and then I'll give you a wave at the end.
Yeah, thank you, Ian. Hi, good afternoon, everyone. Thank you for joining this session, and we just have a great panel about building AI capability in Australia, in New Zealand, and we got 5 different scheme like autonomous AI, physical AI, bio AI, and creative AI, and agentic AI. So obviously, I hope you can all get funded by the government, or you can work together anyway. So for my talk today, I'm going to talk about our AI and accelerated computing, how it can help healthcare and life science. Obviously, we talk about health and life science, but actually the different scheme of the AI, you might find the application inside this talk as well. So I'm sure maybe everyone heard about NVIDIA, and we are known for building chips, building GPUs, and we also build like you might see some very small system like a GP10, which is at a Xenon desk, which you can run a model development environment. We're also building a system at a digital system and also the very large scale full rack solution. Of course, on top of the hardware, also build a lot of the software libraries. You might have heard about the CUDA, and apart from CUDA, which is program environment, we also have a collection of library. We call together CUDA-X because we have hundreds of libraries, and then now we also have a lot of AI models for healthcare, for all different models altogether to enable you to build all sorts of applications. We do build a lot of application framework to enable your building AI applications. So for the healthcare and the life science domain, I think this is the 3 pillars of NVIDIA's work currently happening. The number 1 is digital biology. So this is we build tools enable you, for example, to accelerate your genomic pipeline, to accelerate your drug discovery pipeline, and enable you to basically gain better understanding about your biology or chemistry or about healthcare. The second part is the digital devices. Obviously, we just talk about physical AI, and in the future, I will think all the medical devices will have AI capabilities. You can think about it, they will be like robotics, but they can interact with your patient, with your doctors, and they can look after the people. The third part is about the digital healthcare, and which I think we talk about the agents, and how healthcare agents can help you, and how the tool to help you to build the agents. So I think before I start, I think I will play a video about some of our work in healthcare and life science.
For almost 2 decades, NVIDIA's accelerated computing platform has helped the healthcare industry use the most advanced technologies to improve human health. In medical imaging, breakthroughs in accelerated computing made advanced diagnostics possible. New devices gave doctors better tools, scan times shortened, futures were changed. As computing advanced, so did the vision. CT scans now capture 4.5 billion times more information, revealing every detail. Accelerated computing made AI possible, and AI enables recognizing problems faster and catching diseases earlier. Now we are at a new frontier where every hospital, patient room, and medical device will embody AI. AI brings precision care to those who need it most. Genomics has advanced from decoding the human genome in days to minutes, turning complex signals into insights. Today, genomic sequences are being designed by generative AI and paving the way for groundbreaking treatments. With accelerated computing, molecules are modeled and simulated at atomic precision. New digital agents help scientists design experiments, develop therapies, and push the boundaries of discovery. Every breakthrough isn't just about technology.
Hi, Maroka. Hi, Anna. It's good to see you again.
It's about people, giving patients the best chance to heal and recover. That's why, together, we can do what's never been done. Accelerated computing, AI, and robotics. Together with you, our partners, we're pushing the boundaries of what's possible. And this is just the beginning.
I think at the core of our innovation, our work we have done to accelerate the healthcare research is the library that we are building. We have built quite a lot of different libraries to enable this field. We have a library to advance the image construction, enable the medical imaging AI. We have projects such as called Matheny. Maybe a lot of people heard about, or even like some researchers at Auckland University are using Matheny to achieve the imaging AI. And we have the tools to enable you to build the training your robotics. We have a project called Isaac Sim, Isaac Healthcare, which enable you to train healthcare robotics. We have a Holoscan, which is our another software runtime, which enable you to process your sensor data and also your image data and many different modality of the information which you can enable you to build robotics. We have another tool called Parabricks, which we can accelerate the genomic processing. And we have a tool to enable you to build the agents and also build the different types of the study of the protein, DNA, RNA structures and design them. I think I will give you some example of our work on the digital health domain. So this is one of the projects we are working with our partners called the virtual cell research. And the idea is, for example, we can build a digital twin of your cell and you can gain better understanding. You can design better medicine to treat any disease that could happen, and you can understand, basically gain a full understanding about which part of the issue, what's the issue, is getting better, getting worse. This problem, actually, virtual cell research is really a data-intensive problem that is very aggressive in computing. So we have worked with a community called SCVOS to develop a data science library called Rapid Single Cell, which enables you to accelerate the virtual cell and single cell research. Here we show actually some number. We show that for one of the harmony of the different cell data, on the GPU, you can achieve up to 300 times faster than run on the CPU. So this enables you to do more with less time that can be more productive. This is another library we worked called equivalence. And in the past few years, we see a lot of advancement in molecular design, protein design, DNA design, but at the core of them, they use one calculation called geometric neural networks, and it's also very time-consuming. So we implemented on the GPU a library called equivalence, and which can achieve, for example, the protein structure studying and the molecular structure studying how to interact. So this library also we can achieve that there is some results that can run 5 times faster when they are running on the accelerating the corners. With the genomics, in this conference today, a lot of people talk about the genomics. At NVIDIA, we have a product called Parabricks. This is actually it's a new record which was achieved at the end of the last year. So NVIDIA worked with some of our partners in Broad Institute and the Broad Clinic of the Children's Hospital and also the Roche sequencing. They achieved basically end-to-end, and from the sampling to get the results less than 4 hours. Actually, this is the Guinness World Record. Behind that one is NVIDIA's Parabricks, which can accelerate the processing of the genomic data. So obviously, over the past few years, we can see that computational biology actually evolved very fast from early stage of the AlphaFold 1, which we understand the pattern of the biology, to AlphaFold 2, which we can predict the structure, and to the AlphaFold 3, which we announced last year, we can basically have multimodal understanding of protein, DNA, RNA, molecular, how they interact, and we enable us to design a biological system. There are different models apart from AlphaFold 3 and also other OpenFold 3 and also other models from the different organizations. So at the core part, we have the libraries such as the equivalence, which can accelerate the computation path. Apart from the library, we also work a lot on the healthcare models. We create a lot of models ourselves, such as the protein which is design or atomic 3D protein structure. We have another model to study the RNA sequencing and to optimize them called a condom. And we also have the other model to, for example, to generate new drug-like molecules. So we created the model, we trained them, and we actually contributed to the open source. You can see them in the Hugging Face. NVIDIA actually is the largest open source model contributor for the Hugging Face. Obviously, the Clara model is actually used by lots of the research institutes, also by the biopharm companies such as Lilly. And what's good from NVIDIA is that we not only contributed the model, we also contributed the data you to train these models so that you can download the model as well if you want to build your own model. So from the talk about the build model, we have a platform called BioNemo. I think they got 3 functions. One is to train your own model, which we have called BioNemo framework, enable you to build your own foundational model if you have your data. So this BioNemo basically can have a different computation mechanism that enable you to, for example, parallelize across a single GPU, multiple GPU, or even multiple nodes, can depend on the size of your model you want to train. The second part is called BioNemo NIM, which is in short for NVIDIA Inference Microservice. We basically have all the model which is optimized, and we can make it downloadable as a container. You can run it on the cloud or run on prem. We have different type of model, and we also have created a BioNemo blueprint. The blueprint is basically the reference gen AI workflow, enable you to build your own pipeline, your own healthcare applications. There is some sample at I think a build.nvidia.com website. We have some examples such as the virtual screening pipeline and also the protein binder design. You can check out at the build.nvidia.com website, and you can find out more information about the different names and all the different blueprints. This is one of the partners which we announced at the end of last year, which Eli Lilly, basically the last biopharm company in the world. They announced last year they're going to actually buy thousands of the B300 GPU to build a digital superport. Of course, earlier this year, NVIDIA and also like Eli Lilly jointly announced we're going to invest $1 billion to build an AI factory in South San Francisco. Obviously, the model we generate actually will make maybe available to the researchers. Apart from the digital biology, the second part were the digital devices. Over the past year, obviously, we have seen the different medical devices, and now AI actually enter into this space to make basically medical device into robotics for whatever, like a medical imaging, digital surgery, and also the healthcare robotics. There is lots of work happening in this domain, and also I'm going to build a tool to enable you to build your medical devices. I think from our perspective, we see the medical device actually in general, for the physical AI for healthcare is a 3 computer problem. The first computer is the training computer, which enables you to training your AI foundation models. And the second one is your simulation computer, which basically enable you to generate the data to train your, for example, robotics to be robotics. The third is the runtime computer, which is basically when you train your model and you want to deploy your model into your real time. So the training model, training computer basically is where you will get your model. Like the example, basically like a medical imaging, we got a Moonlight model which you can train, and they are much more being developed. The second computer for the simulation computer, we got a software called Isaac Sim and Isaac for healthcare, which enable you to generate the research data to train your robots. And the third part basically is the runtime computer. We got another tool called HoloScan. They got lots of software SDK enable you to build the runtime, build your data processing, and enable you to build your basically medical device with the physical AI capabilities. And the third part, I think I will talk about the agent, which because just a panel, we just now we talk about the agents. And actually for the healthcare, obviously, it's also a domain which we can re-innovate the healthcare domain. You can have the agents to, for example, doing the medical scripting to enable to the post-procedure care about your patients. And for example, you have a mental health agent to enable you to engage with your patient. They are much more, and this is a huge opportunity for the healthcare domain. At NVIDIA, basically, we built a tool to enable you to build the agent, and for the healthcare agent as well. Basically, we have a tool called Nemo, which including all the functions from end to end, such as data curation to customizer to build a model, and also we have the guardrail to enable you to make sure the model is safe and secure. But of course, if you want to find out more information, we're going to have a conference called the NVIDIA GTC conference, which is going to happen in next month. If you want to scan the code, you can find out how to register and access. The conference will be a hybrid conference. You can attend in person or you can attend virtually. You will find out more interesting about healthcare and about AI in general, about all the different ways that we're doing AI, which we have discussed in the panel. Thank you. So and also my colleague Gabriel at the back will be here. If you've got anything you want to talk to us, feel free to reach out. Thank you. Any questions?
Time for a question. Well done, 15 minutes.
Okay, thank you. Yeah.
Do you have any questions? Don't be shy.
I was interested in your names.
Yeah.
How do you train them?
That's a great question. If we technology speaking, the name is just containers. Container basically you can pack the different function software inside. So we optimize that one. That means you can get a better performance possible. And then you can download to your environment or you can launch in a cloud. It's available in different public clouds such as AWS. Also, you can ask the university to download it for you. You can run on your laptop. Even you can run, for example, maybe some of our partners, they show the DGX Spark or GB10 machine. You can run on that one as well. Yeah, we're gonna I think, Sean run on that. They got a 2 DGX Spark, and they can run the name on that platform, and they got a very good performance.
Yeah. Cool. All right. So once again, thank you.
Okay, thank you. Yeah.
We'll try and catch up over a coffee because there's some really cool healthcare applications.
Yeah, definitely. Thank you.
All right, so keeping the pace cracking along, next we've got Noel. He's going to talk to us about, I'm excited about this one. I think there's primates in there somewhere. All right, cool.
Go for it. Oh. How does this work? Kia ora, can you hear me? Is this working? Oh, excellent. Cool. Tēnā koutou katoa, ngā mihi o te ahiahi. My name is Noel. I'm from the Centre for eResearch at University of Auckland. So part of my job is partnering with researchers to create technical solutions for their research questions. So that's doing data analysis and visualizations. So today I'm here to talk about a project I've been working on with Dr. Nicholas Malone from anthropology. So he's a primatologist who is interested in the online buying and selling of primates like orangutans and monkeys. So I'm going to be sharing some, our work and also our experiments with large multimodal models, also known as vision language models. I just want to touch on my title a little bit. Thank you for coming to my talk, even though it sounds a little bit hippie. It's like models of loving grace. So it's actually a reference to, can I do that? How do I go to the next slide? Sorry.
No, on this one.
Oh, thank you very much. Yeah,
These are forward and later.
so this is the name is borrowed from a poem by the American writer Richard Brosigan. So he wrote this during the counterculture era in the 1960s. So that might explain the hippie language a little bit. I thought it was fitting for the work. It kind of talked about this, he had this very optimistic view about technology that it was going to create a utopia where people, machines, and nature can coexist. It's not going so well at the moment. So just to get you situated, our area of focus is Indonesia. So it's a highly biodiverse area of the world. There are more than 40 different primate species there out of a total of 200 around the world. And here's just a few. See if you can spot the selfie monkey that was famous back in 2011. Unfortunately, a lot of the primate species there are in decline. So they are all threatened with extinction. There's a lot of causes for why they're in decline. Just to name a few, there's deforestation, loss of habitat, I guess contact with humans and conflict. But what we're going to focus on today is the, I guess, poaching or, I guess, hunting of these primates for the purpose of keeping them as pets. Now, if you guys got the idea that this might be a good idea, the unlikely event, primates are not good pets. They require a lot of attention and enrichment, and when they grow up, they are large and aggressive. So that's actually how a lot of them get abandoned. And in Indonesia, unfortunately, it's kind of seen as a status symbol. I should say, though, that there's a lot of conservation organizations, NGOs, who are working on, who are from Indonesia, and they're working on the ground to sort of reverse this culture and reverse the decline. So traditionally, well, in the past, they've been sold in, these primates have been exhibited in sort of cages along with birds in the urban areas of Indonesia. So these areas are called pasar burung, or bird markets. But I guess in more recent times, the sellers have been a bit more shy about showing them in the markets due to enforcement from the authorities. So what we found is that actually if you go online in social media and marketplace sites, you can actually find these primates for sale, these individuals for sale. And you can, and later on in this video, you can see that like in the comment section, they're haggling over prices. And you know, you can sort of DM or private message the sellers for, I guess, information. So we decided to sort of do a bit of analysis or a bit of collection to figure out what the extent of this trade is and the kind of individuals that are being sold, the species that are being sold online. So we sort of came up with 39 keywords. So they're sort of just search phrases in Indonesian around buying and selling primates. One is beli monyet, which means to buy monkey. We did an initial collection of posts in June, which gave us about 5,000. And that's because TikTok limits it to only have 110 posts per search keyword. So we repeated that by doing a daily collection between September and to November, where we search for all those keywords to see if there are any new videos, and that netted us a lot more videos. And there's potential to collect more of these posts from other social media and sites as well. We just chose TikTok because there's an existing tool for collecting it. So this is what we were expecting when we did the searches. These are kind of, I guess, posts where these are offers for primates. And we thought when we searched those, we were just going to get like tens of thousands of these. Unfortunately not. So it's full of a lot of typical social media posts that might have a partial keyword match, or TikTok just thought, we'll put it in there for engagement. So one way we could sort of sort through this is to go through all of these posts manually to see if they are about primate trade or not. Fortunately, they are well-studied tasks in computer science. So they luckily, you know, for example, if we want to extract text captions from the cover image, you know, that's called optical character recognition, and there's heaps of different methods for doing that. So machine learning, and in particular deep learning, has made a lot of progress in solving a lot of these tasks. However, a lot of the pre-trained models, they work for a rather narrow range of inputs, and it requires significant time and knowledge to adapt those pre-trained models to put them into work for what we have. And not to mention, we need to combine those different models for different tasks to sort of produce an overall decision on whether it's a trade post to sell or not. And we're not sure, given that we've seen all this irrelevant stuff, we're not sure how prevalent the posts were going to be. So this is where the large multimodal models come into the stage. So the idea is that these models are trained on ginormous amounts of data. As we've heard yesterday, it's an indiscriminate collection where there's the good, bad, and ugly that's on the internet, and very little respect or ask for consent for whether they should be collected. Nevertheless, they are, they have been evidently been improving in the last few short years. So the promise of these models is that instead of applying a specialized model for each of the tasks, you can just shove everything into the model, ask your questions, and you get your answers. We decided to sort of test that out. So we thought we'll apply one of these models to our research. So the commercial offerings like ChatGPT Pro didn't have approval to process sensitive research data at the time in our institution. So we couldn't just, buy a license and use that. We chose to use an open source model called Quinn. At the time, the version is 2.5. And then in September last year, there was Quinn 3 that came out. And then just 2 days ago, there's Quinn 3.5. So things are moving really, really quickly. We fit in about 9 gigabytes of the post description and cover image along with this prompt, basically asking, do you see a primate in that cover image? What do the captions say in the post? And do you think it's a primate that's being traded? So we ran that on a A100 GPU, and the final run took a bit more than 100 hours. The model found that 13 out of that many were likely instances of primate trade, and is also in Indonesian. The majority of them were macaques, and it took about 19 kilowatt hour of energy just spent by the GPU. So we haven't tracked the CPU and the cooling and what energy that consumed. So just to give you some context, that's about 1 day of the average New Zealand household's energy consumption. So when we started looking at the results that came out with, it looks great. It seems to have understood the captions on the cover image, and that seems right. But as we look on, we saw some issues. That's clearly not a long-tailed macaque on the cover there. So we did a bit more systematic sort of evaluation. So I went through 326 video posts, and just to see how well it's done in some of the tasks. So we found that it was relatively good for judging whether the language used was Indonesian, and whether it showed a primate on the cover. And also, it was actually pretty good at figuring out whether it's trading primates. But we found that of all the ones that were marked as primate trades in Indonesian, only about 63.4% agreed with my evaluation. But nevertheless, it was still a useful sort of, I guess, narrowing down of the initial number of posts. So some of the reflections, it was a good tool for this particular situation, we thought. It meant that we didn't have to build this pipeline to sort of get some initial results. And because it narrows it down to a small number, we have like a human in the loop to make sure that the results are correct. And it was pretty resilient to the messy nature of text and images on social media because it's seen it all before when it was trained. It was able to handle emojis and slang and hashtags, which I've seen problems with in traditional natural language processing tools. Some of the other things, they resist the seductive nature of convincing responses. So I find that when you're just doing spot checks in the responses you get back from the model, it can build a false confidence in you. So it's better to sort of more systematically sample it. In terms of next steps, we'll probably improve the pipeline and collect from a few different sources. We're also open to any ideas and your expertise. Thank you very much.
Awesome. What an amazing presentation. And I think the first presentation I've seen here, which actually told us how many kilowatts you used to train the model. I would love to hear more on that because we're talking a lot about GPUs. And I hear energy in the news all the time at the moment. Yeah. We've probably got time for a question or two. So has anyone in the room got a question?
Was it easy to identify a suitable model?
We chose Quinn it was pretty good in some of the benchmarks. So if you look at some of the image processing benchmarks, then yeah. But it's always, we used the Transformers library, which pre-packages a lot of different models. So you can just, write a few lines of code and load a different model, and you can always try it yourself. Yeah. Yeah, well, yeah, I tried a couple more specialized models. I don't know if they're more traditional. So there's another model called Segment Anything, and that is more specialized. Even though it's a transformer-based model, it has, I guess, a smaller sort of data set that it's trained on. So it's just doing image segmentation. So we ran that against all the covers in there. It did uncover a few that the Quinn model didn't see, but then the Quinn model also saw some that it didn't see. So I don't know if it was a wash. Yeah.
Cool. All right. So maybe is Nick here? So Nick's next. So maybe while Nick, if you get yourself wider, if there's time for let's keep cracking on. Thank you to the two presenters who got the slightly longer 15-20 minute slot. So we now move into 3 lightning talks. And there's actually, I don't know if you're spotted in the program, but we actually go down the bottom and then along just to freak me out a bit more and trying to chair this lot all in 1 hour. So I really appreciate on that last slide, thanks to Nick, and then straight into Nick. So wonderful timing, and over to you, Nick, and I'll give you some comes up in a couple of minutes.
Thanks, Richard. Hi, so I'm Nick Young. I work at the Centre for eResearch, same as Noel, in the solutions team as a research software engineer. And so like Noel, I support researchers here at the university with their assorted research IT needs, including this kind of thing. So machine learning solutions to their research IT problems. So in my 5-minute lightning talk, I'm just going to briefly take you through a project I worked on over the last year or so with a researcher called Professor Paula Lodgley, and she's from the Health Economics Department, which is the joint department between here, the Faculty of Medicine and Health, and the School of Business. So what Paula was interested in is New Zealand's Givealittle crowdfunding platform, which is an online platform where anyone can submit a campaign and request funding. Specifically, she's interested in the health causes category within Givealittle and how people receive funding there, who receives funding, and if anyone, the demographics of who receives funding, and to see if there's any sort of disparities there in terms of fairness in Givealittle. So this is what the homepage of Givealittle looks like. You can see there's a fair bit of funding that goes through this website. And if we look at the health causes section specifically, you can see there's some campaigns listed there on the left. And if we look at under the hood of how this page works, it uses a JSON-based API. I've got Google Chrome developer tools here on the right showing the JSON from that API. So you can see there's JSON objects there, one for each campaign. And you get 10 per page, and you can do a maximum of 1,000 pages, which means we can get 10,000 campaigns from Givealittle in JSON format. So I wrote a Python script, technically it's a Jupyter notebook, some Python code to extract all of these campaigns, and then for each page, go and visit the page, extract some more information about that particular page, like the start date, the end date, how much they raised, what their goal was, the title, the description, and in that JSON we actually get the hero image. So we have all of that information. My code outputs all of that to an Excel spreadsheet because that's Paula's preferred format for this kind of tabular data. So I sent Paula that Excel spreadsheet and she said, great, this is great. I'm going to get my master's student to go through this and start manually classifying for each campaign the person's name, age, gender, ethnicity, etc., other things. And she uses the term coding here, literally assigning codes. But I was thinking perhaps instead of coding, we could do some coding. And by coding, I mean Python programming. So I had a try with initially Llama 3.2, but over time I've moved to Qwen 3 VL. So like Noel mentioned, that's a multimodal LLM. So I can feed it both the text and the image, and it can draw conclusions from both of those things together, putting together clues from both of those. So for instance, for determining ethnicity, it can look at both the image and the text, and if there's clues in one or the other, it can put them together. So here's my Excel spreadsheet. You can see there's a bunch of data there. Yeah, that's Qwen 3. That's the Hugging Face page. There's some example code, which is what I used to get started with using Qwen 3. And on the top right, that's how you load Qwen. It's pretty simple, just a couple lines of code. Transformers makes this very easy. And you can just swap out that model name with whatever other models you want to try. And in the bottom left, you can see some example Python dict data structure extracted by Qwen. And some of that stuff is quite subjective. I just wanted to see how Qwen would handle those kinds of subjective things, just to see what would happen. And so then once we have all that extracted, we can start fitting, for example, a linear model and start trying to do some statistical analysis to try and answer that initial question of, is there any statistical significance here? And if you look at this model, it's pretty bad. That R-squared is terrible. Those p-values, not great either. But I'd try and reframe that. It's not that the model's bad per se. It doesn't really matter what your age, gender, ethnicity is on Givealittle. It doesn't really affect your campaign success. And by campaign success, that's the amount you raised out of your goal, so the target completion percentage. So yeah, positive outcome there, in my opinion. But yeah, depending on which model you use, you might get a different answer. All of this is open source, by the way, on this GitHub organization, UA eResearch/Givealittle. If you want to have a look at that code, so both my scraping code and my LLM inferencing code, that's all open source. And because this pipeline is pretty generic, you can reuse this for any other task. So here's another task where I use the same sort of pipeline. In this case, I'm looking at Google Street View images, so those are extracted from Google. And here's So it's a photosphere, so it's a 360-degree photo, and I'm feeding that in this case, Llama 3.2, and asking it to extract some information about the environment that it sees in this 360-degree photosphere. So what type of environment it is, how many cars do you see, how many people do you see, that sort of thing. And I've also used Qwen 3 Omni. In this case, it's multimodal and supports video and audio simultaneously. So I've been making it watch reels off the internet, in this case from TikTok, Facebook, YouTube, etc. And then again, extracting some information about those reels. And I want to give a shout out and thanks to Nectar for enabling this research by providing me with an A100, particularly Sean. Thanks, Sean. And that's all. If you have any questions about this, feel free to come and talk to me. I'm here today and tomorrow. Thanks.
All right, cool. So just in time, so we're going to go straight on to the next presentation from Anju. So there's a microphone here. If you can get yourself wired up, that would be cool. Thank you, Nick. I have to say, I am really enjoying this conference. So can you pop that on? And last year we saw Rick Stevens give a keynote about where I guess the AI was a year ago and where he saw that we were heading. And it's great to start to see this kind of this thing about some of the unhobbling gains that Rick talked about. So last year nobody talked about Qwen. This year we've got 2 back-to-back presentations talking about it, which is really cool. So would love to keep the conversation going over into the break. Next up, we've got Anju, who's going to be talking about a quite different project, but one a bit closer to PHF, and yeah, titled Community Health and Wellbeing Profiles. And I'll hand over to you.
Thank you.
Yeah, cool. 6 minutes, I think we can hand it up.
Yeah. Hi everyone. My name is Anju. Today I'm going to present my project called Community Health and Wellbeing Profile System. This project was completed with PH of Science as part of my master's program at University of Canterbury. Yeah. In New Zealand, wellbeing data spread across multiple platforms like census, police, environmental models, satellite data. Each side requires different skills, tools, and format. This makes it difficult for decision makers to combine all this data and extract key insight. To solve this problem, to address this problem, I built an automated data pipelines that combine all this data and calculate indicators, build composite score, and produce maps, charts, and many summary tables. And finally, my system produced a consistent community well-being profiles for every territorial authority in New Zealand. This is I got the idea from this one. The public already part of Public Health England already did this project. Richard worked on that project. And these are the data set that I actually used in my project. The census 2018-2023, the victimization data, ERFI, land climate data, MODIS and EVI, the gap model, PM 2.5, Sentinel 5P, nitrogen dioxide, air quality data. And these are the actually system measures. I divide like this. Housing quality, living situation, socioeconomic condition, these are the 3 core census domain, and all others are added more context on my project. And first, the system worked like this. First, I download the raw data from the website and define many Python functions for treating suppressed and missing values, standardized names, geographies, and build indicators. And first I calculate indicators at SC2 level, then aggregate them into TA level, and save into geo packages, and produce maps and charts. And the pipeline is work like this. I divided the divided the whole project into different modules, and each folders were different sections and fully automated. I defined the configuration files, and there is nothing hard coding. And this is the main important thing. There is a Word template defined there, and it's a Microsoft Word template. Use the docs.tpl Python library. We can create from the placeholders and the headers replaced with the actual the graphs, the TA names and the values. We got the final report like this. And this is one example for the table generation. That's the template, and after rendering, we got a table like this. And we extend this project like this. We can add more geographies and add more domains. We actually plan to do a Microsoft Word add-in and generate reports there, and integrates into large language model. The summaries are automatically generated using the AI. I've successfully transformed the raw data into a unified system and produce a consistent report, territorial authority report for all New Zealand. I also did a Streamlit dashboard. We can do like this. Thank you. Thank you so much.
I think. All right, so I think we'll just keep moving forward so that we can try and get to that 3 o'clock afternoon tea. But very keen to say for each of the lightning talks, please do talk to everybody in the break. I didn't have time at the start to just kind of acknowledge that. One thing that's here where I work at PHF Science, I think one of the most rewarding parts of my role is actually mentoring students. In the last 2-3 years, I've been able to mentor students from most of the New Zealand universities' data science programs, and it's great to be able to have 2 of my students here at the conference today and tomorrow presenting. So well done, and talk to us in the break. I'm going to hand straight over now to Sean, and same thing, so let's go.
That's great. Hi, I'm Sean, Center for eResearch again, here to talk today about scalable, efficient AI nodes. Those that know you, so this is, I'll get to the name, but the classic problem, at least in our university with GPUs, whether it's underneath somebody's desk or whether it's a virtual environment, on-prem cloud or public cloud, is how do you share this effectively? In addition to having to stop and start workflows, you've also got kind of bringing down code. Every GPU environment and AI environment is different with different packages and CUDA versions and everything else. It's fairly bespoke. And it's generally not very portable. We've used Nectar at University of Auckland. We did have a reservation system where a researcher could reserve a GPU for a month or 3 months. And that works, but it's not very efficient. It takes like an hour to snapshot and an hour to rehydrate. It's certainly not efficient. So this aims to tackle this problem. On the name, I hate naming things. Those who have been around me know that I don't like wasting a lot of time, and I do think sometimes it is wasting time naming things. So we didn't hold this up. We just gave it a kind of a funny name, just to get it off the ground. And as it is, sometimes those names kind of stick when they get embedded in code and images and everything else. So it was kind of unexpectedly successful as a POC, and I'm sure it will be renamed, but there's been a lot of jokes with this around the office, I should say. And there is a history with AI MLDL with different advances being named after people. So coincidentally, I'm lucky there. So this is the abbreviated stack. I mean, it's a really complicated stack, but we're leveraging existing technologies at the University of Auckland. We've got a bare metal server that has GPUs, OpenStack hypervisor, that's all standard configuration. We've got a Magnum, which is OpenStack's Kubernetes deployment and management module or project. We've got Kubernetes pods on top of that. We're using Hammy Scheduler. There's a bunch of different schedulers out there for scheduling GPU resources in Kubernetes. We found that Hammy, which is really kind of brand new, does this the best because it can effectively hard partition fractions of GPUs, and it can do it dynamically. And that's really, really cool to do that without MEG or any other kind of commercial partitioning. There's a scheduling user dashboard, which I'll show you, and it spawns Jupyter notebooks. So onboarding, you can log in SSO to Akiri. You can request an allocation. We use service units. A lot of cloud resources use service units. That gives the researcher the freedom to choose. Do you want a big GPU for a small amount of time or a small one for a big amount of time? And of course, you can request for more, but it kind of keeps some accounting there. Okay. So once you're logged in, you can launch a Spot notebook. You can choose, there's multiple GPUs. You can do this heterogeneously. You don't have to add like a whole node of GPUs on the back end. You can just use one GPU from the cluster if you want, or many. Or you can schedule a date in the future to launch this. In the calendar, you can see when other people are blocked out, and you can reserve your time. Once your time frame is current, then that yellow thing that you probably can't read will turn to active. You can click launch, and in about 5 or 10 seconds, it will launch. We can do fractions of GPUs, like I said, which is really cool. I'll give you a proof slide after this. And we've got a number of GPU images. There's no one GPU image or AI image, of course. It could go on forever. We're just to get it started, we'd love to have like a container repository where you could submit your own kind of image, and then you could pull it down in here. That's kind of on the to-do list or the dream list. This is an A100 80 gigabyte GPU with a 25% fraction, and that's maxed out right there. So it really does work well. It respects the bounds of both CPU and RAM in the background, the Hammy scheduler. User metrics, we found that it's really hard to measure as a researcher, as a user, exactly how much you're using. And we've got built-in live metrics here. We've also got an after reservation review. And we've got some scheduling hints, or some utilization hints built in. For example, in the right-hand graph, you're using a lot of CPU, which is the blue bar, and the turquoise bar is memory. So it's got a suggestion down there. Maybe next time you can use a flavor or a GPU that uses a lot less memory to be more effective and efficient. It's really important as admins and service owners to have really good metrics to show back to stakeholders that the service is really being used effectively. We haven't been able to do that effectively with GPUs in the past. This is something that's really a groundbreaker. It's also good as admins of the service to be able to manage different allocations and say to the researcher, well, you requested this much, but you've only used this much. And it's kind of a really good transparency thing. Current and future, it's just a POC now. This isn't a big service that we've launched. It's probably insecure. It probably has some teething things that we need to go through that's really brand new, last minute. But we'd love to get some beta testers, expressions of interest. If you want to have a chat in the hallway, happy to chat. Happy to share code and collaborate. Every single part in this is open source and GitHub. And we still have some usability hurdles. It can't mount university storage. It's hard, kind of clunky to get data into it and out of it. There's solutions there. We just need to spend a bit more time. And we're working on apps. So in addition to Jupyter, you can launch, Chat GPT windows, translation, MFlow, different things like that. So the future's really endless, and everything kind of snaps in modularly, which is really, really super cool. You weren't able to do this 2 years ago, I don't think. So that's it. Please reach out. Keep in touch.
That was awesome. I want to put my HPC guys in touch with you. So 3 o'clock. Okay, cool. So guys, I'm just going to say thank you everybody for the session. Each of the speakers, I think, will be hanging around or up in the atrium. Please do talk to them. Make the most of being here today and tomorrow. If you're still here by the graveyard slot tomorrow, I'll see you at that. Thanks.